Well, this will be a video you might want to be pausing and rewinding from time to time since it's a brand new concept, brand new topic. Actually, we have talked about linear approximation before, taking a tangent line to a graph, tangent line to a solution curve, and approximating its value using the tangent line, not knowing what actually the true equation is for y equaling f of x. But the scenario we talked about in class was that given the curve y equals f of x, we have an exact value, one exact value. So it's like our initial value problems where we will be given a differential equation, and we're given an initial value, and you're asked to use the tangent line approximation to approximate the value of the function. Okay, so this scenario here, if we want to approximate the value of this function when x is equal to 3, we find the equation for the tangent line, which all we need for that is the slope of the curve at that point, so the slope of the tangent line, and then we need the point that it goes through. So we can come up with an equation for the tangent line, and using that, y equaling something, we would get plug in the new x value that we want to approximate it at, and we'd find y at that x value. So approximation for f of 3, the exact f of 3, and there will be an error in there, and the error, big or small, doesn't really matter. We're doing our job approximating the value of the function using the tangent line. So there is a method called Euler's method. Please don't call it Euler's method, which I've heard students say, but it is Euler's method, just like the Huntington Beach Oilers, and I'm very sorry about that one. Anyway, from the practice worksheet, you were given two sides of a worksheet during class. One side had a bunch of integration problems where you'd use formula, u sub, or parts, and it didn't tell you what to use. But then the other side of that was a worksheet for practicing Euler's method problems. And we're going to start with number 41, it's the first one on the list. It actually starts off by a slope that's kind of boring, but we'll get to that. So the scenario is that the derivative of y with respect to x, so the derivative of this function is equal to x minus 1. And we're given an initial value when x is 1, y is 2, and so we have the point right there on the curve. Now the only thing we know about this curve, well, two things. One, that it actually goes through that point, and we know though that the slope at that point is 0. Well, how do we know that? Well, let's go ahead and look at this chart over here, and we'll get to that. The current, or sometimes I refer to this as the old xy, that's our current xy, and the xy in this case would be 1, 2. So we're going to fill out this chart. This is the chart you're going to want to use when we're dealing with Euler's method. Okay, so the current, or the old xy, is 1, 2, and the slope, we're going to find the slope at that point, and the slope at that point is given to us in the equation, the initial equation here, which is dy dx equals x minus 1. So this is going to change from problem to problem. You're not just going to do the same thing every time, but this slope is x minus 1. So if the x minus 1 is the slope, then we take the x coordinate and we subtract 1, so we get the slope is 0. That's what I was meaning by when I was saying it was boring, because probably a better example if I found one that wasn't just 0. But nevertheless, let me walk you through the process, and then I will explain why that is the change in x. By the way, I didn't make mention of this yet, but our goal for this particular problem is to approximate the value of the function when x is 1.3, but we're using a step size of 0.1. Okay, so in other words, we have to figure out what the approximation of this function is when x is equal to 1.3. So 1.3 is right about there. We have to take a couple steps before we get there. Okay, we can't just jump all the way to 1.3 and plug that in, finding this equation for y. We have to go to 1.1, then 1.2, then 1.3. Okay, so again, I'll walk you through the process, then I'll kind of backtrack and see. I want you to see the whole process, and then we'll fill in some details later. Okay, so the new y, this is the new y, because again, we have an old y, which is 2, so it's 2 units high, but we want to know how high it's going to be when we use the tangent line approximation to approximate that. So the new y is equal to the slope, which is 0 in this case, multiplied by the change in x. Now it doesn't really matter what that is at this point, but it will, plus the old or current y1. So where are we now? Well, we are 2 units high right now, and so our first approximation, at 1.1, would be 2. So our new coordinates are, like we're trying to build this function, are 1.1, okay, comma, because that's our, we added 0.1 to our old x, and then we get an approximation of 2. So that becomes our new xy. Okay, so that we bring it all the way over to the front of the chart here, and now our current xy is 1.1 and 2. Okay, so now we need to do this whole thing again. In fact, we're going to do it twice because we have to get to 1.2 over here, comma something, and then 1.3, comma something. Okay, and that something right there is going to be our approximation of the function at when x is equal to 1.3. So I just have to take a couple steps before we get there. Okay, so our slope now, at this point, we're going to recalculate our slope as if the point 1.12 were actually on the graph. Okay, we're actually on the curve. But in fact, 1.1, which is right there, we are right here right now. And in fact, we're going to pretend that we're right there. So in other words, we really don't know where the function is, where the graph is when x is 1.1, but we have an approximation for where the graph is when x is 1.1. So we're just going to use those two coordinates and the same equation for the slope to calculate our new slope. Okay, so our new slope is our current x, or old x, minus 1. And that 1.1 minus 1 is 0.1. Okay, so our current slope is 0.1. Our new y is going to equal our current slope multiplied by our change in x, which is again 0.1, plus our current y, or our old y, and that's 1.1. Okay, so we have 0.1 times 0.1, which is 0.01, and then if we add to that 1.1, we get you gotta be careful here, 1.11. Okay, so that becomes our new y. That's how high we think that the graph is at that point, or when x is equal to 1.2. So that becomes our new y. Now we repeat this one more time, and we will have our goal of approximating y of 1.3. Okay, so we're at 1.2 now. We think it's a certain height of 1.11. Oh, what did I do? Sorry, I messed up. I knew that didn't sound right. Oh, 8, almost 9 minutes. Oh, that's a bummer. Alright, so you guys probably saw that I did this. Let's see if I can fix it real fast. Okay. You know what? Let me stop the video since we're already at 9 minutes, and I will come back. I knew I did something wrong, so sorry. I will come back.